Hello everyone. Are the slides visible?
Yes, sir.
Okay. Okay. So last class I ended at this gave the second order Cauchy-Euler ordinary linear differential equation. So how to solve the approach whenever like we have a differential equation, second order linear differential equation where we have a non-constant coefficient in front of the second order derivative. So we have a particular approach to solve this kind of differential equation where we just take x is equal to this independent variable, we just approximate as exponential t, and then we just solve it. So in last class I discussed this. So and then we finally find the solution. So based on that, many of you are new. So in this phase, so this question I covered, although I covered in last section, last phase one, but still you can just give a try. Right now, you can just this is a question which happened in GATE 2019. So the question was for the differential equation d2y by dx square minus n plus 1 y upon x square is equal to 0, where n is some constant, then the product of its two independent solution is. So it's just a Cauchy-Euler differential equation, as you can see. If you just take x squared, so you can just rewrite it in this form. So which is nothing but it's a Cauchy-Euler linear differential equation where you have a non-constant. So I would just request you so that you can just solve this question. It is little lengthy. You can take time and provide the answer. Like one of the four options is right. So you have to find you will get two solutions, and first and second, and then you have to just do the product of these two solutions. So you'll get one value. So you can just start by using this approximation. Same approach. You find x, you just approximate this, then find dx by dt. Eventually, you have to replace this dy by dx by some constant, and x dy by dx, and this x squared d squared by dx squared you have to replace with some constant. Like constant with I mean coefficient should be constant. So using this approximation, you can just start. So how many of you can think that you can solve this question? And if I can just ask frankly. Hello? Are you solving, like, everyone? Today attendance is less, only 7 people have joined. Oh, okay. So I just, to those who have just joined, I've just given this question where you can just try and solve this question. You can solve this question using the Cauchy-Euler approach, which I discussed in the last class. Many of you are joining right now. Okay, okay. So I think Chaudhary has written I cannot solve it. Okay, so since what I will do is I will just solve this question for all of you so that you can solve more questions, because last class I didn't solve any questions. Okay, so you have this kind of form. Whenever you have this kind of second order linear differential equation, the first thing, as I discussed in the last class, you approximate that. Let x is equal to exponential t. Then you just write, you can just write dx by dt is nothing but exponential t. And then apply chain rule. So from here you can get dy by dx is nothing but 1 upon exponential t dy by dt. Okay. Now what you, this is, suppose this is equation 1, this is this is 2. Now what you do is that you just find the second derivative, because at the end you want to replace this term with some constant coefficient times d2y with something like that. So you take the derivative, again you take the derivative of equation 2 with respect to y. So you get dy dx of dy by dx, dy by dx of 1 by et dy by dt. So just taking the derivative with respect to x on both sides of equation 2. So this, now again you can apply chain rule. So d by dt of this particular quantity in brackets times dt by dx. So just applying chain rule. Now you can just apply the product rule, because this is one, this is second. So just apply the product rule. So you get something like this: dy by dt, and dt by dx is nothing but, from here you can write 1 upon dt by dx is nothing 1 upon exponential t. Now from bracket you can take out this exponential t common, so you will have e to the power 2t, because already we have one exponential t and one exponential t you will take out. And in bracket then you're left with d2y by dt square minus dy by dt. This is nothing but d2y by dx square. Now take this thing on the left hand side. So exponential 2t is nothing but x square. You take, so you, if you take e2 to this side, you just get x square d2y by dx square, which is nothing but this is nothing but the first term of this linear differential equation. So that's what you needed. You wanted to replace this variable with some constant term, which you see here there is constant 1. So you just replace this, you just put this 3 in back into 1. So you will get what? You will get d2y by dt square minus dy by dt minus n plus 1 y is equal to 0. Now this is general form of any second order linear different ordinary differential ODE, ordinary differential equation. Okay, this is second order. So the general method to solve second order linear differential equation is you approximate, let us assume the solution y is some exponential r times t. This is the assumption which you make when you solve any second order linear differential equation with constant coefficients. Then you just calculate dy by dt. So you will get r exponential rt, and then you again calculate d2y by dt square, r square exponential rt. Clear? This, I think this is clear up to right now. So now you just put these values back into this equation. So d2y by dt square is r square exponential rt. dy by dt is r exponential rt minus n plus 1 y is exponential rt. Now you can take exponential terms common. So you're left with something in bracket r square minus r minus n plus 1. Now you know by the definition of exponential that if you just so this can never be equal to 0. It's always greater than equal to 1. So exponential R2 cannot be equal to 0. So the quantity in bracket is equal to 0. So this quantity in bracket is equal to 0, and this is what we call auxiliary equation or something like this. And when you solve this auxiliary equation, you'll get the roots. Since it is a quadratic equation, you'll get two values of R, and that two values of R you can just put in and you'll find the final solution. Now this is a little tricky because you have to make some arrangements in order to factorize it. So one trick is that you just you can rewrite, if this is equation 4, say if this is equation 4, you can just rewrite this form. With R you can just write n plus 1 minus n, because n cancel, so it will just be, these two equations are 4 and 5 are identical. I've just tried to rewrite in this form. Why? Because it will be clear. Now just take common, so it will become Rn plus 1 plus Rn minus n plus 1, 0. Now you can just take R common from here, so from this and this, so left with R plus n, and then you take n plus 1 common, minus n plus 1 from this equation, from this and this point, so we can get R plus n. Just factorize it. Now what you're left with is R plus n and R minus n, R minus n minus 1 is equal to 0. So you've got two solutions, R is equal to minus n and R is equal to n plus 1. So these are the two solutions two roots which you got, and hence we know that the solution y can be written as the linear combination in this form, exponential. We know that for any second order linear differential equation, if we have two distinct roots, distinct means they are different and they are real, in that case the solution is this form, C1 R1t plus C2 some C1 C2 some constant R2t, where R1 and R2 are roots. Suppose this is R1, this is R2. So you can just write C1 exponential minus nt plus C2 exponential n plus 1t. But you have to be careful because in our original case we have take this approximation where x is equal to x per et. So since x is, we can just write this as this form, C1 upon e to the power nt plus C2 e to the power n plus 1 t. Now since e to the power t is equal to x, so x to the power n is nothing but e to the power nt, and x to the power n plus 1 is nothing but e to the power t n plus 1. So we can use this in here, and we can just replace C1 upon exponential nt is nothing but x to the power n, and exponential n plus 1 t is nothing but x to the power n plus 1. So this is your final solution. So the final solution is a linear combination of two independent solutions. So the first one is 1 upon xn, and the second independent solution is x to the power n plus 1. Now in the question they have asked that what is the product of these two independent solutions. So the product is nothing but 1 upon x to the power n into x to the power n into x. So it is x. So this is the product of the two independent solution of this second order linear differential equation. So the correct answer of this question is B. So this is the way through which you can solve this Cauchy-Euler differential equation. So is it clear now? This question is clear to everyone. Any doubt, any place, you can just ask me right now. Okay, clear to me. Clear. What about rest?
Yes, sir.
Okay, okay, okay. So I think it's clear. So one or two more questions were there related to this topic, which I covered in last. So you can just go and solve those questions. So now I will come to another topic which I was not about to teach, but since it was raised in the last class, so in order to explain that, I have to give some background. So now I'll be talking. This is related to solving second order linear differential equation only, but of special kinds. So, the topic is solution about singular points. Now, those who have attended last lectures, like where I covered complex analysis, also in that we know what are singular points and what are those. But again, I will just revise it. So, so what is first of all what is singular points? Then we can talk about solution. But what is singular points? So suppose you have some equation, differential equation, d in this form, general form d2y by dx, so second order differential equation, plus some p1x. So in that case, these coefficients p, if p1x and p2x are not analytic. By analytic, it means if p1x and p2x are infinity at some point, x is equal to a, then a is called the singular point of that equation. A is called the singular point of that equation. Okay, so you just put the value of a in this coefficients, and you find that if it is equal to infinity, that it is blowing up the this p1x p2x. Then you say that it is a singular point. By singularity, it means it is undefined. So the solutions are undefined at that point. Now two more parameters are defined: q1x, which is nothing but x minus a times p1x, and q2x, which is x minus a whole square p2x. These are singular points, but if you just calculate these quantities, x minus a times the p1x and x minus a whole square times p2x, and if these quantities q1x and q2x are analytic, by analytic I mean that it means that they're not equal to infinity at a, then a is called the regular, this is terminal, regular singular point. And all other points, for example, in if I take p1x and p2x, and for all other values other than a, where p1 and p2x are defined, that is, they do not have infinity, those points are called ordinary points. So those points which are not called singular points, they are, its complementary thing is ordinary points. So ordinary point are those points where we have finite value of p1 and p2x. Okay, so these are some definitions. So what is the application of these definitions? So first of all, before going into the application, we can just take a simple example where we have simple equation, that second order linear differential equation, you have to find the singular points. So this is equation, you can just convert it in the general form. So you can also do with me at the same time if so. Sorry, x plus 3 y upon x square x minus 2 so to 0. Okay, so I just divided x square, divided the whole equation by x square upon x square x minus 2 whole square. So I think this is what we'll get. Now this is P1x. Your P1x is 2 times x minus 2 x square x minus 2 whole square, and P2x is the coefficient of y, which is x plus 3 x square. Now you're both, as you can see from this equation, that P1 and P1x is equal to P2x is equal to infinity at x is equal to 0 and x is equal to 2. If you just put x is equal to 0 and x is equal to 2, so you're getting infinity. So they are not analytic. And since they are not analytic at x is equal to 0 and 2, they are called the singular points. So these two, x is equal to 0 and 2, are these singular points of this equation. Now you have to find whether they're regular singular points or not. So you just find q1 and q2x. So just take case for x is equal to 0. Your q1x is what? X minus a is 0 here, because I'm taking singular point 0. So x minus 0. Just I'm following this. So you have to find q1x and q2x. So, and p1x is nothing but 2 times x minus 2 upon x square to the whole square. So you'll get some 2x minus 2 x upon x minus 2 whole square. Now when you put x equal to 0, you are getting infinity. So q1x is still not analytic. So it is the value of q1x still infinity x equal to 0. So x is equal to 0 is a singular point, but it is an irregular singular point. Okay. So this point is called the irregular singular point. Similarly, when you calculate for x is equal to 2, for x is equal to 2, when you calculate q1x, so it will be x minus a is 2 times p1x, 2x minus 2 upon x square x minus 2 whole square. Okay. Now this x minus 2, this cancelled out, so it will 2 upon x square. And then when you put x is equal to 2, you're getting some value which is not equal to infinite. You're getting 4, maybe 1 by 2, which is not equal to infinite. So similarly, you can also calculate q2x and you will find that it is also not equal to infinite. So x is equal to 2 is then called the regular singular point. So there are two steps. First of all, you have to find that what are the singular points. In that, you just find it by calculating p1x and p2x, and from there you can find what are singular points. Then you can find that what are the regular singular points. Now, significance of this, why we find regular singular points, because when we solve some special kind of differential equations, there we get this regular singular points. So as in the last class, we were solving a Legendre's differential equation, which is in this form. Okay, this is a Legendre differential equation, if I'm not wrong. 1 minus a. So this is a Legendre differential equation. Now you just convert it into this form, general form. You just divide all the terms with 1 minus x square. N plus 1y is equal to 0. Now your p1x is 2x upon 1 minus x square, which is not defined. It is equal to infinity at x is equal to plus minus 1. If you put x is equal to 1 or plus minus 1, you will get p1x is equal to infinity. So this x is equal to plus minus 1 is this singular point of this equation. And you, when you find q1x and q2x, they will come out not equal to infinity at x is equal to plus minus 1. So that will prove that these points are not only singular, but these are regular singular points. So the point, so the main significance is that at x is equal to plus or minus 1, the solution of this differential equation is not defined. So the solution of this legendary differential equation is not defined at x is equal to plus minus. That is a significant singular point. So now there is a way to solve this, how to solve this legendary differential equation. So what we do is that there is a Frobenius method. So this method is used to solve this kind of differential equation. So it what it says is that if suppose if you have some singular point which is x naught, suppose if x naught is a singular point, regular singular point, while you solve for some differential equation, then the solution of the differential equation can be written as this form: exponential k ak xk, and then there is another term which comes here, which is x to the power r. So what Chaudhary was doubt was that this legendary differential equation, it has singular points only at plus minus 1, and x is equal to 0 is an ordinary point. Ordinary point where it means that it is defined at x is equal to 0. Then why we are using this? So the thing is that this is a general form. So the only thing is that if there is some singular point which is x naught, and this x naught should not, it's not necessarily that it equal to 0. It can be anything. It can be any value. It can be 0, 1, minus 1. In all that case, the solution of this differential equation can be written in this form. This is nothing but some kind of Taylor series or this kind of thing. So, hello, hello. Yeah, boss. Okay, so this is the way. So I will not going to. So that was a point. So that this differential equation is not having any singularity at x is equal to 0. Then the doubt was that this general solution is valid only when we have some singular. No, this is not. This is valid for all the values x naught. It's not necessary that the singular value is at 0. Then only you will define this form.
Sir,
Yes.
sir, if there's a singularity at points other than x10,
Hmm.
then the form will, isn't it true that the form will be x equals to x to the power r summation of k, a k x minus a to the power k, where the a is the singularity?
Uh, Solution will be what? Y is equal to summation.
Uh, x will be replaced by x minus a.
X will be replaced by
So
x.
that was my question. So we shouldn't, we should have the have to consider the form as x to plus one or minus one. Isn't it true?
This is the general form, so you there is no need to replace the r with minus. That okay? You're talking about r with minus r.
No,
X.
x by x will be replaced by x minus a, or a is the singularity. In case of legendary, plus or minus one will be replaced by a, x minus a.
Yeah. Because that's the singular point, right?
Then why we took this form? We shouldn't have take x to the power r summation of k, a k, x minus a, x plus or minus 1 to the power k. Isn't it true?
Yeah, suppose if you don't have, okay, so suppose if you don't have this equation, and one more thing which I was, this is Frobenius method is used. This is slightly different with the power series method. When the power series method, we don't have this term xr, right? We only have this kind of thing, right? Hello?
So this is only true when x is ordinary point. There's no
Yeah,
regular
this is,
singularity present.
yeah, this is only true when x is ordinary point. But when x doesn't have some singular point, then in that case, this equation is valid. That's what I have learned.
Yes, but this is only true when you have regular singularity at x equals to 0. But when you have regular singularity at x equals to other points, you have to replace x by that x minus that point.
So if you're replacing x with x minus r, you're saying that, right?
Yes, sir.
So you're taking to a descending power, something like that, right? Descending power of x.
Yes, if x equals to 5 is a regular singularity, then this equation would be y equals to x to the power r summation of k a k
Mhm.
x minus 5 to the power k.
Okay, okay, okay. Okay, fine, fine. Yeah, but that thing is clear now, that how to find the, suppose in the last class also there was one
Yes,
question.
sir. Yes, sir. Thank you.
Yeah. So in the last class there was one question. So yeah, in this question. So in this question, there was, you have to find that at what points the solution will diverge. So this is straightforward. You don't need to remember these complicated solutions. You just reduce this in this form, d2 by dx square. So this will become something like d2 by dx square minus 2x 1 minus x square plus some here will also come, and you just see that for x is equal to plus minus 1, these are the singular points for this differential equation, so the solution will diverge. So for, you can also remember that for legendary equations, because this is general for legendary equation, so at x is equal to plus minus 1 the solution will diverge. So no need to remember these complex these things. So, okay, so now what I will do is that I will solve. I was. It was very hard to find any question in GATE exam from Bessel function. I only found one question. So the Bessel function is also quite. The approach to solve Bessel equations are also quite similar to what we did in legendary equation. The general form of Bessel equation is x squared dt by dx squared. This is the general form of the Bessel function equation. So here also you can just easily find that the singular point of this Bessel equation is nothing but at x is equal to 0. So x is equal to 0 is a regular singular point. And the general solution of Bessel equation is also like it is composed of two independent solutions. So the general solution can be written as a linear combination of these two dependent equations. This plus n and minus n comes because when you solve using this Frobenius method, you will get something like when you equate the coefficient equal to 0. What you do is that you first approximate the solution in this form. You find the derivative dy by dx, then again find d2 by dx, put in this original equation. Then you find for different values of are like different values of power of x, you just equate the coefficient. And when you do that, you'll get something like this. So you get two roots, m is equal to plus 1 minus 1. For these two values, you get two independent solutions. It is a very lengthy like solution, so that is not required for your exam. You can always look in some books. So someone has asked which book should see. There are many good books also. Okay, for referring for differential equations. So you can for general like preparation point of view, you can, if you want to just go into the basics, some simple in which is explained simple way, you can refer to H.K. Das by mathematical physics H.K. Das. It's an Indian author, so it's easy to understand. And there's some foreign authors also, I'll just tell you. And for preparation, if you're trying to prepare for GATE exam, the best thing is to solve previous year questions of all the like exams. Just take 20 year question and then solve it. So that will be good. Okay, so this is a general form of the solution of the Bessel function equation. It also has two independent solutions. So this is not important. What is important? Solving some of the questions related to Bessel function. So in GATE 2008, there was one question. The question was consider the Bessel equation, a special kind of Bessel equation, which is this form: d2y by dz square plus 1 by z dy by dz plus y square to 0. So this is nothing but if you just multiply both sides with z square, you will get something like this. Which is just your original Bessel equation form. Okay. But here your n square is 0. This term is 0. So this special kind of Bessel equation. So they have asked that which one of the following statements is correct. You already know that second this it will have kind of two independent solutions. So first of all, in order to solve this question, first of all find the singular points. So you just take, this is P1Z. So the P1Z is 1 by Z. So at Z is equal to 0 is your first singular point. You will just find it is a regular singular point. So the option A, that equation has regular singular point at Z is equal to 0 is fine, but at Z is equal to infinity, it has finite solution. 1 by infinity is some constant. So Z is equal to infinity is not, sorry, Z is equal to infinity is not a singular point. So the option A is wrong. So what you'll do is that in order to solve this kind of question, I will give a trick. Otherwise, it will become a little lengthy if you solve using conventional methods. So what you do is that you just find the coefficient, you just take the ratio, coefficient of dy by dt, dy this term, second term, divided by coefficient of d2y by dz square. Coefficient of dy by dz is 1 by z and coefficient of d2y by dz square is 1. So it is 1 by z. And this is infinity at z is equal to 0. So z is equal to 0 is a singular point. Solution is not defined. It is not analytic. Z is equal to 0 is singular point because it is non-analytic at this point. And then you find coefficient of y divided by coefficient of first term d2y by dz square. This coefficient is 1, 1. Both coefficient is 1. So it is something, some constant. So solution. So what I'm doing is that this represents one class of solution. This is represents second class of solution. So one class of solution is defined at every point except z is equal to 0. Because at z is equal to 0, the function is not analytic. It is singularity exists. The second class of solution is defined at all points. There is no singularity. Therefore, your final solution will consist of some, say, two independent solution. These are just, I have just taken some common, you can take any value. So where suppose the second class solution is represented by this. So this independent, this and both these solutions are independent to each other, And this solution, because it is defined at all points, which is given by this, which is not given, but you can just, it is a trick method through which you can say that it is defined at all points. So it is defined at all points, or it is as in the question, it has an entire solution, something like it has an entire solution. And the second form of solution is not defined as defined at z is equal to 0. The second class of solution is not defined at z is equal to 0. So uh, equation B says that equation says two linearly independent solutions. This is right, but they are entire. No, we have seen that only one class of solution is defined at all points. The second class of solution is not defined as z is equal to 0. So B is also not right. C is saying that equation has an entire solution and a second linearly independent solution is singular at z is equal to 0. That means out of these two, one solution is entire, it is defined at all points. The second solution is defined at all points except z is equal to 0. So C is the correct option for this question. So this is just a trick way to say that if you have been asked that what kind of independent solutions are there. So this is the way through which you can say. Okay. So this is the only question which I got from Bessel function. So and now okay. So what I was thinking is that do you want me to solve some more differential equation questions? Like, because I've not covered basics, which I've already covered in the last session. But since if any of you want me to cover, I can do that. Like one question from different kind of a first order linear differential equation and those things.
Excuse me, sir.
Yes.
So you said that the Legendre solution should not be defined at plus minus 1. But in the last class we saw that it has two solutions. One is P and the other is Q. And we saw that the polynomials were all defined at plus minus 1. So is it the Q part which will not be defined?
Yeah, it will be Q part. That was more detailed way. Okay, so in the last class, I just gave two solutions, right? P and Q both. So the where it is gone. Yeah. Yeah, so the Q part has this not defined part, but I think that is not required when you're solving questions in gate less time. So even if you're just knowledge of how to solve the questions about the singular points, so you can just by doing this, you can just find that okay, x is equal to plus minus 1, we have some divergence.
Okay, sir.
Like this is a differential equation, right? d2 by dz square plus 1 by z dy by dz plus y plus y is equal to 0. So your p1 of z is 1 by z and p2 of z is equal to 1. So actually this kind of this p2 of z, p1 of z is nothing, this coefficient of dy by dz by dt by dz square, this ratio is nothing but actually giving p1z, and p2 is nothing but this coefficient of y, and the second ratio is nothing but represents p2z. So so we know that from this p1z that at z is equal to 0, there is a singular point, so there is no solution at z is equal to 0. So one class of solution will have, so whatever solution you have, since one more thing, since it is a second order linear differential equation, so it will have two class of independent solutions. So suppose some independent solution is suppose z to the power something, another is some other, some function of z you can consider, f2z, f1z. Now these solutions, the first class of solutions will certainly have this kind of structure where it is not defined at z is equal to 0. So one is this. But I'm not. What I think is that second class of solution consists of points which is defined at all values of z. Like at all values of z, the solution is defined for second class of solution. And what you can do is that you can just assume this using Frobenius method, I think. You just try this Frobenius method. You just try to plug in this y. You just calculate y dash. You just calculate y double prime, and then you just try to put in back into this equation, and then try to calculate the coefficients. So what you will get is that suppose you are going to solve this general way. So you will have something like this. When you calculate y prime, y double prime, and put it back into equation, you will get something like this. Suppose some z square exponential k, something like m plus k, m plus k minus 1, some z to the power something like some z to the power something here. Then again you will get some value. Okay, something like this. You'll get something like this. Now, when you solve this equation, what you will do is that you will first of all you will try to find the coefficients, because you need to find the coefficients so that you can just put back those coefficients into this general solution, and then you can just run the summation over. So here it is z, so z to the power m plus k. So the main motive is to find this coefficient. So this coefficient can be found by just putting different values of suppose here you have m plus k. So what you will do is that I'm writing the final equation because I think I have it there. So it will get something like this: m plus k whole square z to the power m plus k plus exponential ak. So this is the final form which you'll get when you will calculate this y prime, y double prime, and put this back into original equation. Now what you will do is that the general way is to you put k is equal to 0 and find, when you put k is equal to 0, then you will have the coefficient to z to the power m. Z to the power m. So coefficient of z to the power m is found by putting k is equal to 0. So when you put k is equal to 0, you will get what? Then equate this because what you have to find is that you have to find all the powers of z, starting from small to bigger powers. So when you put k is equal to 0, then you get z to the power m, and the coefficient you equate it to 0. So you'll get a to the a 0 and m is equal to 0, m square, sorry. So here you'll get some m is equal to 0 from here. Then again you put you need to find the second highest order, which is z to the power m plus 1. So you put the coefficient of z to the power m plus 1 is equal to 0. So you'll get something like a1 m plus 1 whole square is equal to 0. And then you'll again put so this is a way through which you solve this question, and I think by solving this you'll get two classes of solution, where one class of solution will be defined at all points and other class of solution will not define at z equal to 0, something like that. I'm not very sure, but what I've tried is to give a trick method to solve this kind of question. And this coefficient thing is nothing but P1z and P2z. So you can just try to relate that how this different P1 and P2z can give you different class of solution. I was trying to find it that does the P1z represent one kind of solution and P2z represent some separate kind of solution? Because if that is true, then we can say, okay, that P1z if represent one kind of solution, it is not defined at z is equal to 0. And so we have, and then P2z, since it is defined at all the points and it represents another class of solution, then we can say that, okay, we have two different sets. But I'm not very sure of this point, so that's the only thing.